Hello folks, so I'm back with another tough integral. You can try it if you are interested in it. Otherwise, I'm going to explain the solution of it. So the question is integral 0 to infinity cos x upon e to the power x plus e to the power minus x dx. And yeah, it is very interesting to solve it. You can see that it is a combination of trigonometric function and exponential functions. The limits are 0 to infinity, so you might not have seen something like that previously, but yeah, do give it a try. So the first step that I will use is I will take a e to the power x common, and basically I will multiply e to the power minus x on both numerator and denominator. After that I'll get this, and if you are asking me why did I do that, so for that you need to be aware with the expansion of or let's say this formula, 1 upon 1 minus z equals to summation k equal to 0 to infinity, and basically the summation of this k 0 to infinity z to the power k, this is not 2, this is z, is equals to 1 upon 1 minus z. If you are familiar with this formula, then you will understand that why did I do that, so that I can write it as a summation form, and that will help me to simplify it. So of course there is a condition that z should be, the absolute value of z should be less than 1, modulus of z basically, and since I am using here using e to the power minus 2x as z, so e to the power minus 2x is also between 0 to 1. You can check the value, or you can draw the graph of e to the power minus 2x, you will see it. So of course e to the power minus 2x will satisfy this formula, so we can move on using it again now. So integral 0 to infinity e to the power minus x, and I am writing 1 upon 1 plus e to the power minus 2x as summation of this, as according to the formula that I explained, and cos x. Well, I am not proving this formula right now, but if you want I can prove it in some other video, but it is not that tough, you can check it out also again. So after that this summation I will take it to the end, left end, to just simplify the expression and see it as a whole. So cos x and e to the power minus this minus x and minus 2kx will summation, so minus 2kx plus minus x, so x comma 2k plus 1 dx. So I have finally this. I can do this summation to the here because e to the power x is not gonna affected by this k, so this is basically a type of constant for this expression, so I can multiply a constant inside that is not gonna affect the summation. I hope you understand that much. Similarly with cos x is also not affected by k. So yeah, these are basics, but yeah, of course you need to be aware of these things. Again, now moving on, I am gonna interchange these two, take the summation to the left hand side and integral to the inside. How can I do that? So it is again fundamental, you need to know that. I may explain in some other video, but yeah, that is a theorem that we can use here, interchanging these two. Again, after interchanging, we can see that this e to the change back e to the power minus x 2k plus 1 cos x dx, and now this here, if you are not aware with Laplace transform for, so then you will not be able to get it, but this is a form of Laplace transform of cos x evaluated at 2k plus 1. So it expands to, it gets to this integral 0 to this whole Laplace transformation of cos x if we evaluated it 2k plus 1. And now move on after that, so that can be written as 2k plus 1 upon 2k plus 1 ka whole square plus 1 using Laplace formula, Laplace transformation formula. So this whole integral can be written as this. So that is the reason I did this simplification, so that I can change it to summation, and after that this summation will get back to this Laplace transform. So that was the logic here. So now this Laplace transform integral will simply reduce to this. Now our integral is basically this summation of k 0 to infinity 2k plus 1 upon 2k plus 1 whole square plus 1. And now again, if you see our integral, now I'm gonna do something in the actual question. The original question was this, I hope you remember, so I'm gonna do something in it for my another step, and this is interesting part. I hope you see this. Well, the whole step are interesting, but this is also very unique step. So the original integral was this. So if you observe that this is a even function. What is the even function? I hope you know that. If we put minus x in place of x, fx is equals, basically fx is equals to f of minus x. Similarly, this is an even function. So since this is an even function, I can write it as 0 to infinity. I can change it as minus infinity to infinity cos x upon e to the power x plus e to the power minus x. This is basically a King's formula that we use in integration, definite integration. I hope you have studied it, but even if you have not studied it, this is we can write it in case of even function, because yeah, basically the King's formula, it is famous with the name of King's formula. But yeah, in case of even function, we can write it as this. It does have a proof, but I am not discussing it today. So again, this can be written as half e to the power minus x. Again, same concept, taking the e to the power x common, and since minus infinity to infinity is a real number, so I have written r for shorter notation. Again, so it has reduced to this. Now in this, I am gonna substitute e to the power minus x as u. So e to the power minus x is equals to u, so minus e to the power minus x, dx is equals to du, and x is equals to ln minus ln u. Since e to the power minus x is u, so x will be equal to minus ln u. So from here I can evaluate the new limits. So for x is equals to minus infinity, u will be infinity, and x is equals to infinity, u will be 0. So our new limits will be from infinity to 0, not 0 to infinity. Keep in mind, infinity to 0, and that is different. Minus sign will be there. So yeah, I hope you understand that much. So our new limits are infinity to 0, and since we are substituting minus x with ln u, e to the power minus x with u, so it will change back to this, e to the power minus x is u, so 1 plus u square and minus ln u, and dx will e to the power minus x, dx will change back to minus du from here. Fine. Now again, cos of ln u, of course cos of minus x is cos x, so cos of minus ln u will be cos ln u, 1 plus u square, and this minus sign will I will use this minus sign to interchange these limits. I will take it as 0 to infinity, and that was I was explaining earlier, that if you integral of infinity to 0 is equals to minus of integral of 0 to infinity. That is another definite integration rule that we use. Again, move on. Yeah, so now another interesting step are gonna come. So what we have here is cos of this. So if you know the Euler's formula, I'm gonna use the real part of cos e to the power I theta, and I'm gonna write cos theta as real part of e to the power I theta using the Euler's formula. Now of course this is the unique step, like how did you go from here to in the complex numbers. But yeah, that is the beauty of tough problems. You gotta use your every weapon in your arsenal. So I'm gonna use complex numbers. So I'm gonna write cos theta as real part of e to the power I theta. So cos of ln u will be real part of e to the power minus ln u. Of course, because if you write minus ln u here, so that will be same as cos ln u is equals to cos of minus ln u. So you can see that I am writing this theta as minus ln u. Okay, now again, if you move from here, e to this ln u, of course this e to, there is a I have missed I here, I missed it, sorry. So this I will move back to the power of u, and this will change since e and ln u, so it will cancel it out, and this will remain as u to the power I, real part of u to the power I. So again, I can write this ln u as, now you know, I will show you. I'm gonna change this ln u to cos of ln u to real part of u to the power I, and this will remain as it is. So basically writing x as u as x, I have changed the variable. So x to the power I upon 1, don't get confused, I am just writing u as x and I am changing du to dx, so that is not gonna affect much here. Fine. Let's move on. Now again I am writing x is equals to tan theta. That is obvious because I have 1 upon 1 plus x square in the integral, this denominator. So of course I am gonna use tan theta substitution here. That is a kind of a standard. So x is equals to tan theta substitution. So tan inverse x is theta, and since integrate both sides, differentiate both sides, so dx upon 1 plus x square will be d theta. Fine. And of course you can evaluate the limits also, new limits. If you are substituting x is equals to tan theta, so at x is equals to infinity, theta will be pi by 2. At x is equal to 0, theta will be 0. Now you know tan theta is tan 0 0, tan pi 10 in basics. Again, now move on. So this will get back to this will change to, after substitution, tan theta to the power I, and 1 upon 1 dx upon 1 plus x square will be nothing but d theta. So now I have this. Again, a tough part is gonna come. So I am writing tan to the power I theta as sin to the power I theta and cos of to the power minus I theta, real part of this. And again, move on. Sin to the power I theta, cos to the power minus I theta, and I am multiplying 2 in the numerator and denominator. So after it will 1 by 4 and 2 here, multiplying 2 in the numerator and denominator. So this basically changes to the beta function, the form of beta function. I hope you are aware with beta function and gamma function. You can check it out if you are not. I'm going to use it here because. So this is basically a form of beta function. So if you write the beta function with variables u and v, so that is nothing but 2 integral 0 to pi by 2 sine to the power 2u minus 1 theta cos to the power 2u minus 1 theta. So if you replace 2u minus 1 with I and 2v minus 1 with minus I, so you can find the new u and v. So 2u minus 1 as I and 2v minus 1 as minus I. So u is this and v is this. Fine. So I will write this whole in the form of beta functions. So it can be written as this. U and v will change to this by this substitution. Again, I am gonna use a formula of beta function, interchanging it to gamma function. So that is nothing but gamma of 1 plus I by 2 and gamma of 1 minus I plus 1 by 2. Now if you are not aware with the gamma and beta function, so you are not going to understand this, so you need to learn that first. I am not going to explain it here because that is not in the scope of this video. So yeah, of course, real part of gamma of 1 plus I by 2, gamma of this upon gamma of this plus this. So this plus this will cancel out and 1 will remain. Again, move on, gamma 1 will be 1 by 4, real part gamma of 1 plus I by 2 and gamma of 1 minus 1 plus I by 2. And now I'm gonna use the Euler's reflection formula on this function, which is gamma of c into gamma of 1 minus z is nothing but pi upon sine pi by z, pi upon sine pi z. So replace I with 1 plus I by 2. So it will become pi upon sine pi into 1 plus I by 2. 1 by 2 plus I by 2. I am replacing z as 1 plus I by whole 2. So put z as 1 plus I by whole 2. So it will change back to this. Again, sin pi by 2 plus theta will be cos theta. So I am going to write it as cos I pi by 2. Again, I am going to write this. Now I am going to use that hyperbolic function of cos, because we can write cos of iz is equals to cos hyperbolic z. And this is another formula that I am using. So this can be written as cos hyperbolic of pi by 2, and now this whole is just a real number. There is no complex part in it because I removed the I using the hyperbolic formula. So we can remove this real part, real function, because this is only real only. So pi by 4 and 1 upon cos hyperbolic pi by 2 can be written as sec hyperbolic pi by 2. So yeah, this can be your answer, but also you can, using the hyperbolic formula, again this can be written as summation 0 to infinity 2k plus 1 upon 2k plus 1 power square. So you can write the answer as this also, or maybe this also. Okay, thank you. That was all.